today's lesson, I'm going to discuss the different types of frequency distributions that we get, and I'm going to explain the differences between them and how they can be constructed. A frequency distribution is essentially a table where data is either grouped into classes or it's represented as individual data values, and the frequency for each class or each unique data value is recorded. A frequency distribution gives us insight into the distribution pattern of the frequencies. There are four types of frequency distributions that we will be discussing: ungrouped, grouped, cumulative, and relative or percentage. Now, to understand this lesson, what you really need to take away from it is how to construct a grouped frequency distribution. If you understand how to do that, then the other three types are relatively easy, especially the cumulative and relative or percentage, as these are just calculated columns that we will add onto our ungrouped or our grouped frequency distribution. To construct an ungrouped frequency distribution, ideally we want to be working with a small number of unique data values. So to explain this, let's look at the following example. 25 residents in a city are surveyed, and the number of pets that each resident owns is recorded. So the table on your screen is showing you 25 data values, where each data value is representing the number of pets that a specific resident from the city owns. Now, if we look into this data set, we can see that there's about 5 unique data values. So that is to say, from all the data values that exist in this data set, there's only 5 unique numbers. Now, given that we have a small number of unique data values, we can go ahead and construct an ungrouped frequency distribution. So to do this, we would draw up a table that has columns for number of pets, tally, and frequency, where number of pets are unique data values. So we're going to list them numerically, 0, 1, 2, 3, 4, and the last row is our total row. Okay, so looking at this, if you've never constructed a tally before, then I'm going to show you how to do that. But essentially, we're going to look at our data set and we're going to identify how many times each unique data value occurs, and we're going to record that using a tally and then converting that to a numeric frequency. So focusing on residents who have 0 pets, if we go into our data set, we see we have 1, and we represent this using a single stroke, 2, and 3. So we have 3 strokes that represent the number 3. Moving on to residents who have 1 pet, we have 1, 2, 3, 4, and 5. Now this is interesting. When working with the tally system, you represent the number 4 as 4 strokes, but you represent the number 5 as 4 strokes with a line through it. And we have 6, so we add another stroke. Now we're going to continue doing this for residents who have 2, 3, and 4 pets respectively. Okay, now that we have our tallies, we're going to use this and convert it into a frequency. You can go ahead and just skip the tally step if it's not required in your class. However, including a tally column makes it easy to refer to your data set and physically count as well as record at the same time. Okay, so converting our tallies into frequencies, we see that we have 3, 6, 8, 6, and 2. When we sum up our frequencies, we want this to sum up to the number of data values that exist in our data set. Because if you think of what you're doing, you're physically counting how many times each unique data value occurs in the data set. So if you have to sum up each of those frequencies, it should sum up to the total number of data values. Interpreting our frequency distribution, we can see that most people have 2 pets, since we have the highest frequency of 8 recorded against the unique data value 2. Moving on to grouped frequency distribution. Now we no longer have a small set or a small number of unique data values. So what we do is we actually construct something called classes. Now before I explain to you what classes are or how we actually construct them, we first need to identify the type of data that we're working with. So there are 2 types of data, discrete and continuous. Discrete data is when we're working with the number of people or the number of books. Essentially, it is data that we can physically count. Whereas continuous data is like weight and height. It's data that we have to actually measure. Now, the reason that we have to identify the type of data that we're working with is because if we're working with discrete data, we're going to construct something called class limits. Whereas if we're working with continuous data, then we need to construct something called class boundaries. Now, there is a difference between the two, and there is a need to come up with class boundaries for continuous data that I will explain when we get there. So to understand this, let's look at an example. 50 people from a book club were surveyed, where essentially these 50 people are reading the same book that consists of 100 pages, and they are being asked how far along or how many pages they've read from that specific book. So in our table, we have 50 data values, and just glancing at it, we can see that some people have finished the book because they have read 100 pages, whereas most people are between 30 to 60 pages, suggesting that they are about halfway. Okay, firstly, we can see that we no longer have a small set of unique data values. There are many different numbers that exist in this data set. So we're no longer working with ungrouped frequency distributions. Instead, we're going to be working with a grouped frequency distribution. Next, we can see that this is the number of pages. So it's something we can physically count, and that tells us that our data is discrete. So now we know that what we're going to construct is a grouped discrete frequency distribution. So how do we do this? Once you come up with your class limits, the steps thereafter are exactly the same. We're going to come up with a tally and a frequency, and that would have constructed our grouped frequency distribution. So how do we come up with our class limits? These are the steps you need to follow. Firstly, you want to calculate your range, and we're going to refer to our range as R. Now, your range is the maximum value that exists in your data set minus the minimum value. So that's the highest number that you can see in your data set minus the lowest number. For our data, that is 100 minus 35, which is 65. So we have a range of 65. Next, we want to calculate the number of classes that we're going to put into our frequency distribution. We're going to call this K, and K is going to be calculated using Sturge's rule. Okay, and Sturge's rule states that K is equal to the rounded up value, so that's what those brackets mean. It's the rounded up value of 1 plus 1.44 multiplied by the natural log of n, where n is the number of values in your data set. So for our data, we have 1 plus 1.44 multiplied by the natural log of 50. Rounded up, we get the answer of 7. The third step is we want to calculate something called a class width. Okay, we're going to refer to this as C. Now, K multiplied by C must be greater than R. So you can physically do this by putting in numbers for C, where K multiplied by C gives you a number that is greater than R. Or you can just use this approximate formula where C is going to equal to the rounded up value of R divided by K. So that's 65 divided by 7 for our data, which gives us an answer of 9.29. Rounded up is 10. So that's important. When you're working with rounded up values, even if the answer was 9.5 or if it was 9.1, it would still become 10. So keeping those values in mind, where we had a minimum value of 35 pages, a maximum value of 100 pages, we calculated 7 classes is what we need to construct our frequency distribution with a class width of 10, and our starting value is essentially our minimum value minus 1. Okay, so using those values, we're going to draw up a table with class limits, tally, and frequency. So this is where the change occurs. Because we no longer have unique data values that can represent themselves, now we're going to come up with class limits. So essentially it's like a range. So we're going to have a lower limit and an upper limit. And what that's going to represent is all the numbers that exist between that lower and upper limit, where the lower limit is included and the upper limit is included as well. Okay, so the first thing you want to do is you want to go ahead and write down 34 as your first lower limit. And then we're going to increment in increments of 10 because that's our class width. And we're going to go down to each row, adding 10 to create the next class limit. Once you've done this, you now have all your lower class limits. To come up with your upper class limit, so that's the number on the right-hand side, we're simply going to take the succeeding lower class limit minus 1. So as you can see, it's going to be 44 minus 1, which is 43, 54 minus 1, which is 53, and we're going to keep going like that until we get our final upper class limit. Just as a final check step, we can see we have 7 classes, we have a class width of 10, and we can also see that the minimum value falls into a class as well as the maximum value. So that tells us that our class limits have been constructed correctly because every single data value has a class that it belongs to. So that's the hardest part. Once you come up with your class limits, we're going to follow the exact same routine that we did previously to come up with our tallies, except now we're not looking for just one single value per class limit. Instead, we're looking for a range of values. So for 34 to 43, we're going to look at values that are greater than or equal to 34 and less than and equal to 43. So going through our data set, we're going to do that and we're going to record the tallies. Finally, we're going to use those tallies and convert them to our frequencies. And as you can see, we want that to sum to 50 because we have 50 data points. Interpreting our frequency distribution, we can see that most people have read between 54 and 63 pages, which tells us that most of the people in this book club are about halfway through the book. And only 9 people, so 9 out of 50 people, have completed the book. Moving on to the next example. Here we have 20 people that were surveyed and their weight that is measured in kilograms are recorded in the table on your screen. So the first thing we notice is we don't have a small set of unique data values, so we cannot construct an ungrouped frequency distribution. Next, we see that each data value is representing a measured weight. So this tells us that we're working with continuous data. So if you remember, I originally said that when we're working with continuous data, we need to come up with something called class boundaries. Now here's the catch. To come up with class boundaries, you first have to construct class limits. So we're going to go ahead and do this example exactly the same as we did for the discrete data. And then when we construct our class limits, I'm going to explain why we need class boundaries, and then I'll show you how to construct that. Okay, so the first step again is we're going to calculate our range. So that's our highest value minus our lowest value. For our data, that's 95.66 minus 38, which gives us a range of 57.66 kilograms. Next, we want to calculate the number of classes. Again, we're going to use Sturge's rule. So that's k is equal to the rounded up value of 1 plus 1.44 multiplied by the natural log of n. And in our case, n is 20, which gives us a value of 5.31. Rounded up gives us a value of 6. Then we want to calculate our class width, and we're going to use the approximate formula where c is equal to the rounded up value of our range divided by our number of classes, which gives us a class width of 10. Okay, so keeping those values in mind, we have a minimum value of 38, a maximum value of 95.66. We have 6 classes that we're going to construct with a width of 10. And our starting value is 38 minus 1, which is 37. So we're going to go ahead and draw that table exactly the same, except this time we're also going to include a column for class boundaries. So we have our limits, our boundaries, the tally, and the frequency. Doing exactly what we did previously, we're going to start with our starting value of 37, and we're going to go in increments of 10 down our table to create all our lower limits. Then to create our upper limit, we're going to take the succeeding, which is the next lower limit, subtract 1 to give us the current upper limit. So that's going to be 47 minus 1 to give us an upper limit of 46, 57 minus 1 to give us an upper limit of 56, and we're going to continue all the way until 96. Okay, so now we've created our class limits. Why can't we just use the limits and construct this frequency distribution? Why do we need boundaries? So I want you to look at your data, and you're going to see that we have decimal values. So that's going to actually give you a little tip, because that tells us that we can possibly have numbers that exist between 46 and 47, for example. Let us assume that we had 46.5 in this data set. Then which class limit would we put it in? And we can see that, in fact, we don't have a class limit that this number would fall in, and we cannot have that because now we can't construct our frequency distribution. So to remedy this problem, we use those class limits and we construct something called class boundaries. How do we come up with class boundaries? So firstly, the class lower limit minus d over 2 is going to give us our class lower boundary. And the class upper limit plus d over 2 is going to give us our class upper boundary. Now what is d? D is the absolute value of the class upper limit minus the succeeding class lower limit. So this probably sounds confusing, and it's really not. So I'm going to use an example and show you just how simple this can be. So let us assume that we have these two class limits and we want to use these limits to come up with boundaries. So first we know we have to calculate d because we need it in order to come up with the boundaries. So d is the class upper limit. So if we're looking at the first row, the upper limit's 44 minus the succeeding class lower limit. So the succeeding class will be the row below that minus its lower limit of 45, and we take the absolute value to get an answer of 1. So we know that d over 2 is going to be half. Now using d, we're going to calculate our class boundaries. So for the first row, our class lower boundary is going to be 40 minus a half, and the upper boundary is going to be 44 plus a half. For the succeeding row, our class lower boundary is going to be 45 minus a half, and the upper boundary is going to be 49 plus a half, giving us boundaries of 39.5 to 44.5 and 44.5 to 49.5. So you might have noticed something interesting. It seems as if the upper class boundary and the succeeding lower class boundary are equal. And that is true, and that's actually what we're looking for, because by doing this, we ensure that our data values will fall into at least one boundary. So when you construct your class boundaries, you want to make sure that the succeeding lower limit and the current upper limit are equal. Okay, so we're going to go ahead and do exactly that and construct the class boundaries for our data. So we have our lower boundaries, and we constructed this by taking the lower limit minus a half. And we have our upper boundaries where we constructed this taking the upper limit plus half. Now, if you're really paying attention to what we're doing, then you might be questioning, what if we have a data value 46.5, for example? Will it fall into the first boundary or into the second boundary? So we're going to hold that thought, and I'll answer it in a little bit, because for our current data, that problem doesn't exist. So we're going to go ahead and construct this frequency distribution, and then I'm going to come back to that problem and explain how we would address that. So from this point forward, it's the exact same thing. We're going to look for all the data values that lie between those boundaries, and we're going to construct a tally. Using that tally, we're going to construct our frequency, and as always, our frequency must sum to the number of data values in our data set. Now we've constructed our grouped frequency distribution for continuous data. And as you can see, I dropped that class limit column because we no longer need it. We only needed it to calculate our boundaries. Okay, so let's address that question. In this case, let's assume that we had 56.5 as a weight value in our data set. So which class boundary is it going to go in? And the answer is it will always go into the larger class boundary, right? And the reason we do this is because the way you read these class boundaries is greater than and equal to the lower boundary, but less than the upper boundary. So that tells us that for this class, 56.5 does not exist because we read this as greater than and equal to 46.5, but less than 56.5. So 56.5 will not exist here. However, for the succeeding class, we would read this as less than and equal to 56.5. Okay, so just an easy to remember tip is always put it into the larger class. Okay, so just altering for if that data point existed in our dataset, we see we now have a frequency of 7, and our frequency summed to 21 because we're now including one additional weight in our dataset. So interpreting this frequency distribution, we can see that most people weigh between 56.5 and 66.5 kilograms. Moving on to the cumulative frequency distribution. Now, essentially, this is just a calculated column that we're going to add on to a grouped or ungrouped frequency distribution to essentially make it a cumulative frequency distribution. A cumulative frequency distribution is going to summarize the data to show the frequency or the count of data values that are less than or equal to the upper limit of the class. Using our previous example where we constructed a grouped frequency distribution for discrete data, we're going to use that already constructed distribution and we're going to add on a column called cumulative. Now, if you were asked to construct a cumulative frequency distribution and you were given data, then you would have to go through all those steps of identifying the type of data you're working with, deciding whether it's going to be ungrouped or grouped, and then actually coming up with the frequency distribution. And then finally, you would add this column. So just to save time, I'm going to skip all of that since I've already done that. And we're just going to work on how we come up with this column. So a cumulative frequency is essentially the sum of. If we're looking at the first row, we're going to add up the current frequency and all the frequencies before that. So for the first row, there's obviously no frequencies before. So the first cumulative frequency is always going to be equal to the first frequency. The second cumulative frequency is going to be calculated by taking 4 plus 6. So that's your first frequency plus your second frequency. And we're going to do the exact same thing going down the table where whichever row we're currently at, it's going to be that current frequency plus all the previous frequencies to give us a cumulative frequency. And of course, for our final row, we want that frequency to sum to our total because think of what you're doing. You're summing that final frequency plus all the previous frequencies. So of course, we need to get that total for the cumulative frequency. And that's it. Now you have a cumulative frequency distribution. And the way we would actually go about interpreting this, if we remember, this data was about book pages. So we can see that 4 people have read at most 43 pages, 25 people have read at most 63 pages, and 35 people have read at most 83 pages. The final frequency distribution that we're going to discuss is the relative or the percentage frequency distribution. This as well, it's a calculated column that we add onto a grouped or ungrouped frequency distribution that gives us more insight into the data. A relative frequency distribution shows the proportion that each class is contributing to the dataset. Again, if you were given this in an example, then you would go ahead and follow all those steps to actually construct the frequency distribution, and then you would add on this column called relative. So I'm skipping that to save time, and we're going to use the example where we worked with weight. So that's the continuous data example. So we have our frequency distribution and we've added on a column called relative. And the way we calculate this column is we take the frequency divided by the total. So for the first row, it's going to be 4 divided by 20. The second row is going to be 5 divided by 20, 6 divided by 20, 3 divided by 20, and of course 2 divided by 20 to give us relative values of 0.2, 0.25, 0.3, 0.15, and 0.1. And you can go ahead and interpret this as it is, or you can convert it to a percentage to make it a bit easier to read, where you simply multiply your relative values by 100 to get a percentage of 20%, 25%, 30%, 15%, and 10%. Now looking at this, we can see that 20% of people have a weight greater than and equal to 36.5, but less than 46.5. 30% of people have a weight greater than and equal to 56.5 but less than 66.5, and 10% of people have a weight greater than and equal to 86.5 but less than 96.5. That brings us to the end of the lesson. Kindly like and subscribe and hit that notification bell to keep learning.